Hello again. So let's continue the calculation or the presentation of the fractional derivative, right? Remember, let us recall that the fractional derivative operator that we defined, right, is defined on the Clifford algebra, 1, 1, tensor the differentiable functions on the real line, right? The image is going to be the Clifford algebra, 1, 1, tensor the differentiable, just the functions on the real line. Okay, so having said that, right, we did the calculation for the particular. So actually, before we go on, the Clifford algebra is spanned by one by the A Clifford number, by the B Clifford number, and by the A wedge B Clifford number. Now, this is not an orthogonal representation. This Clifford algebra has an inner product, right? But this decomposition is just a vector space decomposition, but they're not orthogonal, okay? So 1 in this case is going to be the identity matrix, right? 1, 0, 0, 1, right? A is going to be the 0, 0, 0, 1 matrix. B is going to be the 0, 1, 0, 0 matrix. And A tensor B is going to, A wedge B is going to be equal to the matrix 1 minus 1 half 0, basically. So yeah, so it's interesting to see this. Of course, they're not orthogonal because these two guys are not orthogonal, but this guy is orthogonal to those two, right? But yeah, so uh, right. So anyways, so what we did is we calculated the derivative operator on a differentiable function, right? So the differentiable function in our extension of scalar setting is going to be equal to the identity matrix tensor the function itself, right? Now, if I apply the derivative operator twice, I get the identity matrix tensor the derivative of the function itself. So in other words, uh, the square of the fractional derivative leaves this space invariant, that is the space of functions. So if you extend a function by scalar, right, to the Clifford algebra, you're really extending, you're doing the identity tensor of that function. So it leaves it intact, right? So now let's look at the genetic definition, right? And remember, in the domain, there is I tensor F plus, in this case, it's going to be A tensor G, right, of X plus B tensor H of X, right, plus, now let's call this, now normally I will do A wedge B, right, but I guess we could do, well, let's just do A wedge B actually, so see what happens times, well, no, let's not do A wedge B, we're going to do, AB basically, right? Which in this case is going to be 1, 0, 0, 0, 1, right? These two guys are linearly independent, right? Yes, they are linearly independent, but they're not necessarily orthogonal. So tensor, so FGH, let's call it L of X basically, right? So this is a generic term, generic term in the domain of extension by scalars, right? So let's see what happens when we apply the derivative operator to it, right? Okay. So the first one we know, right? So I guess it's just a matter of doing this, right? So this is equal to A, remember, zero, the identity here, and then the derivative over there, right? So if we calculate derivative operator A, you get 0, the identity ddx 0, acting on 0, 1, 0, 0, from which we get 0, 0, right? Plus 0 plus the derivative here, basically. Yeah. Right, that's that operator right there. So it's going to be 0 I ddx 0, 0, 1, 0, 0, from which we get the identity over here, 0, 0, 0, 0, right? And dx 1 half AB is equal to dx 1 half AB in this case is going to be, well, let's just do it slowly so that we can get it done. Yeah, AB in this case is 1, 0, 0, 0, 0. So we get 0 ddx 0, 0, 0. Okay. Okay, now we got that part done. So we get the following basically. So this is equal to 0 f prime 0, right? Plus, in this case, it's going to be equal to 0, 0, 0 dx acting on, in this case, it's going to be the identity gx, right? Yeah. So let's call it g of x, basically. Plus the identity 0, 0, 0 h of x plus 0 d of x 0, 0 acting on L of x. So I get 0 f prime 0 plus 0, 0, 0 g prime of x plus h of x 0, 0, 0, 0 plus 0 L prime of x 0, 0, 0. So we get the following result. The fractional derivative of a genetic term, right, is given by this matrix basically. So h of x, f of x, right, get f prime of x plus L prime of x and then g prime of x, basically. So that is the definition of the fractional derivative of a genetic term. It clearly belongs to a mixture of differentiable functions and functions that of a real variable, right? So they're not necessarily differentiable anymore. So yes, so does h need to be L of x? Does h need to be differentiable? Let's see. No, h does not need to be differentiable. Anyways, yeah, so that is what it is. Now let's consider what happens when we do e to the minus x, right? E to the minus x, the fractional derivative, right, is given by e to the minus x minus e to the minus x 0, right? Which is equal to, I can pull out the e to the minus x, right? And I get 0 minus 1, 1. And this is nothing more than e to the minus x minus the J matrix, right? Where J squared is equal to minus the identity, 2 by 2. So it's a root of unity, right? So yes. So in a way, this is equal to I basically, right? So remember the result that we had first? So it makes sense. Let's see what happens when we do the derivative of 1/2 e to the minus e to the ax, right? Then this would be 0 e to the ax, a e to the ax 0, right? So we can pull out the e to the ax and we get 0, 1, a 0, right? Right, so what is this function e to the 0, 1, a, right? 0. What happens when I multiply this matrix 0, a, 0, right? I get a on the top, right? And I get 0, 0, a times the identity, right? So this matrix, right, let's call this capital A, right? Has the property that a squared is equal to a times the identity, right? So it's otherwise known as the square root of 1/2 times the identity. So yeah. So it checks actually. Remember that this was equal to a to the 1/2 times e to the ax in the previous definition. Well, in the matrix formulation, it has a similar answer. So yeah, so okay. I hope this helps. It's an introduction to fractional derivatives by the method of a scalar extension. So we're extending the scalars from the reals to a Clifford algebra where the fractional derivative becomes well defined. Just remember that these matrices will mimic complex numbers or real numbers or just matrices in general. So question is, can you formulate the the cubic root of the fractional derivative or the quartic root of the fractional derivative? If that doesn't have a problem, hopefully someone figures it out. Thanks. Okay.